Probably you will be able to understand what I'm trying to say here. So let me just draw it and then we can discuss. So this is R2 is given as 0.08 meter. And the temperature here is 100 degrees Celsius. This entire thing, there are two layers are there. So this is one, this is one, and this is two. So this is 2. Thermal conductivity is also given. So K2 is 2 and K1 is given as 5 watt per meter degree Celsius. So this is what is been given. This thickness is given. This thickness is 0.15 meter. 0.15 meter, and this thickness is given as 0.2 meter. So this is, let's say, L1 and this is L2. Our direction is this, so our X is varying in this direction, okay, from this edge. Okay, so what is being given in the problem is there is a frustum of the cone is given, and this frustum of the cone is made up of two material, layer 1, layer 2, and again the heat transfer is taking place in an axial direction from right to left. So heat transfer is taking place from this direction to this. This is the heat transfer direction. And again, what is been given is the radius on the right hand side end is R1 equals to 0.18 meter, whereas the radius on the left hand side end is R2, that is nothing but 0.08 meter. Again, the temperature on the right hand side is 200 degrees Celsius. Temperature on the left hand side is 100 degrees Celsius. There is no heat transfer taking place in a radial direction because there is a insulation material is applied above this cone. So if you look at this particular cone, this is looking at as a rectangle from the screen now. But if you look at in an axial direction, you will see a circle. Okay, so it's a cone which has been cut at two places. Okay, clear to everyone? Is it clear to everyone?
Yes, sir.
Now what is been asked in the problem is you have to find out the temperature distribution in the both the layers of this cone. Okay, so temperature distribution along the axial direction. Remember, whenever we have seen such cases, the heat transfer was taking place in a radial direction, be it a cylindrical geometry or be it a spherical geometry. There we have seen the heat transfer in a radial direction, but here the heat transfer is taking place in axial direction. That is the difference. Okay. Again, as we move along the axial direction from x equals to 0 to x equals to L1 plus L2, the radius of the cone is going to decrease, isn't it? So on the right hand side it is R1 and on the left hand side it is R2. Correct. So that means what? The heat transfer area, which is nothing but the axial area, is decreasing. Correct. So clearly we need to make a shell balance here to find out how the heat transfer taking place through this system, isn't it? So one need to make a shell balance. So please make a shell balance. Is it clear to everyone what I'm saying? Since the heat transfer is taking place in a axial direction from right to left, my heat transfer area is what? My heat transfer area is a cross sectional area. So which will be nothing but the area of the circle, isn't it? If you look at any particular location, and that area is going to change as I move from right hand side to left hand side, because my radius is changing from R1 to R2 if I move from right to left. So clearly my heat transfer area is varying, and therefore I need to make a shell balance, even though there is no accumulation term and there is no generation term, but still we have to make a shell balance. So please make a shell balance and then we will move to the next part. So can you please do a shell balance? Hello?
Yes, sir, we are doing.
Okay. Correct. So input to the shell is going to be area into flux at the location X, isn't it? So that can be given as, suppose at a particular location X from the right hand side. Remember this is 0 and we are moving along this direction, along the left hand side. So consider any location X at which we wanted to put a shell, and there the area into flux at particular location we have to find out. So area at that particular location is going to be what? Pi r square is going to be the cross sectional area into flux. So flux in this case is going to be Qx at the location X, isn't it? Similarly, what will be the output? The output in this case will be given as, again, area into flux, and so that will be pi r square Qx at the location X plus delta X. Correct?
Yes, sir.
So there is no accumulation. Accumulation is 0. Accumulation is 0. And generation is also 0. And generation is also 0. So what we are going to get? Input will be equals to output. Correct? So based on this, what we can write down is pi r square Qx at X should be equals to pi r square Qx at X plus delta X, isn't it? We can rearrange this equation. So by rearranging, what we are going to get is r square Qx at X plus delta X minus r square Qx at X, and again I can divide this by using delta X, and this should be equals to 0. Correct. Remember why I am not getting rid of r square here? Can anybody tell? Why I
Because
am
R
not?
is variable.
R is a function of x.
Correct. R is a function of x. Yes, yes. That is why we are not, getting rid of this r square here. Okay. So in a differential form, what we are going to get from this is d by dx r square qx should be 0. Correct. Again, from Fourier's law of heat conduction, qx will be given as what? qx is given as qx is given as
So minus
Minus k
KDT by
dt by dx.
dx.
correct. So minus k dt by dx. Okay. So now let us look at this equation number 1. Equation number 1 we can integrate easily, isn't it? I can integrate the equation number 1 easily. So what we are going to get is from 1 r square qx is given as r square qx will be given as c1. Correct. So from this qx is given as c1 by r square. c1 by r square. This is equation number 2. Isn't it? Now here this r square, remember here this qx we can put it as minus k dt by dx, isn't it? So then again we have to find out how the t is varying along the x, but on the right hand side we are having a r term, isn't it? And clearly r is related with the x. So just by looking at the geometry of the system, we can find out how r and x is related, isn't it? How r and x is related. Correct. So the relationship between r and x can be directly obtained from the geometry. So that can be written as so let me just rephrase it slightly in a different manner. Okay, let me just do this again. Okay. So I am just rearranging these equations little in a different manner. So what we are going to get here is d by dx minus k r square dt by dx equals to 0. So what we are going to get from this is k, we can take it out because uh, k is basically a constant value here. So we can write down this as d by dx r square dt by dx minus sign also we can get rid of. So this becomes 0. So after integration, by integrating what we are going to get is dt by dx is given as c1 by r square. So that is equation number 2. Okay. So this is just a slight rearrangement of what I have written earlier. So I have got rid of even k because right hand side is 0, so it doesn't matter, isn't it? So that will be the effect of k will be embedded here in c1, isn't it? Correct. Okay. So now, as I said, in this function, I cannot go ahead with further integration because now r is also a function of x, and that functional relationship I have to write. Then and then only I can integrate it further. So just by looking at the geometry of the system, from the geometry of the system, we can directly write down as R is given as, where R is the radius at any location X. So that can be given as R1 minus R2 divided by L1 plus L2 into X, isn't it? So this is how we can write down how R is related to X. So remember, R1 is the radius on the right hand side, R2 is the radius on the left hand side. So the difference between that is going to be the net decrease in the radius divided by the total length. So that will give me how my radius is decreasing as I am moving from R1 to R2. And if that is multiplied to the X and subtracted from the R1, that will give me the radius at any location, isn't it? So all the values are known to us, so we can put all the values here. So R1 is 0.18 minus 0.18 minus 0.08 divided by L1 plus L2. L1 is given as 0.2, 0.2 plus 0.15 into X. So after rearranging, what we get is R is obtained as 0.18 minus 0.2857x. So let's say this is equation number 3. So is it clear to everybody so far? Is it clear to everyone?
Yes, sir.
So now I can go back and solve equation number 2, isn't it? So equation number 2, now I can write directly in terms of x. So dt by dx is given as C1 divided by 0.18 minus 0.2857x whole square, isn't it? So now this clearly, this equation has the variable x. Now we can integrate it easily. By integrating this equation, what we get is so we can integrate this equation for block 1 and block 2. So I am just writing down for block 1. For block 1, we can write down this as integration of dt1 is obtained as C1 integration of dx divided by 0.18 minus 0.2857 x square, and this is for 0 to x between 0.2, correct? So this is for block 1. So by integrating, what we get here is T1 is given as C1 3.5 C1 divided by, I'm just directly writing down, so 0.18 minus 0.2857 x plus C2 plus C2, and this is in the range 0 to x 0.2. Is it correct? This equation is correct? Is it correct? So we are looking at the temperature distribution only in the block 1, and that temperature we have denoted by T1. Is it okay? Similarly, for block 2, we can write down. For block 2, we can write down.
So
Block
there
2.
should be C1 also in the equation.
C1 I have written here. You can see.
Okay.
So for block 2, we can write down the same expression as T2 is given as 3.5 C3 divided by 0.18 minus 0.2857x plus C4, and the constant C, the range here is 0.2, 0.2, correct? So here constants C1, C2 and C3, C4, these are the constants corresponding to block 1 and block 2. We have to find out these constants by putting the boundary conditions. So let us look at the boundary conditions. So what are the boundary conditions here? So boundary conditions I am writing down again. So boundary conditions here are when x equals to 0, when x equals to 0, when x, just wait. When x equals to 0, the temperature T1 is equals to 200, isn't it? Similarly, when x equals to 0.35, temperature T2 is 100 degrees Celsius. So these are the two boundary conditions. Third boundary condition is at the boundary of both block 1 and block 2, that is nothing but at x equals to 0.2, T1 equals to T2, correct? Again at x equals to 0.2, the continuity equation has to be satisfied and therefore minus k1 dt1 by dx should be same as minus k2 dt2 by dx. Okay, so these are the four conditions. Four unknowns are there. We can easily find out the four constants based on these four boundary conditions given. So can you find out the constant C1, C2, C3, C4?
Yes, sir.
So is it clear to everyone what we are doing? Is there anyone not able to get it? So if something is not clear, please ask me in the tutorial class, because otherwise, uh, it becomes difficult for me to, keep on checking on you in the regular class. But in the tutorial class, if you have any doubt, anything is there, you can ask me. Okay. So if you do all your calculation, what you should expect it to get is, I'm writing the final answers. Please check whether these are correct or not. Okay, so C1 expected to get is minus 2.119. C2 is expected to get is 241.2. C3 you will get as minus 5.297, and C4 you are expected to get is 331.74. Just check whether you all are getting the same values of the constants or not. So these are correct constants.
Yes, sir, we are talking about it.
Okay. So now let's move to the questions which are being asked in the tutorial. What was the first part? The first part is we have to find out the temperature distribution across both the blocks, isn't it? Block 1 as well as block 2, or a layer 1 and layer 2. Okay, so we have to find out what will be the temperature distribution. So once you know the temperature, this constant C1, C2, C3, C4, you can put it in the equations given above in these two equations and find out how T1 and T2 are distributed across the as the length x is increasing. So we can write down that. So part A is nothing but the temperature distribution. So temperature distribution is given as, so I am writing down the final equation. Just check whether you all are getting the same expression or not. 241.2 minus 41.2 divided by 1 minus 1.587x. So this is for block 1 and this is for x varying between 0.2. Similarly, the temperature distribution in the second block is what you are going to get is T2 is given as 331.74 minus 103 divided by 1 minus 1.587x, and this is between 0.2 to 0.35. So these are the two expressions which you are expected to get. Are you all getting the same? If you rearrange all the values, you should get these two expressions.
Yes, yes.
Okay, now in part B, if you go back and check part B, what is been asked in part B? In the part B, the question is, I can go back, go up, and then we can.
You can answer in the meeting.
Okay, so the rate of heat flow through the assembly is been asked. So what is the value of capital Q that is been asked? The rate of heat flow through the assembly. So Q we have to find out. So we can do that easily. We can do that easily because the temperature distribution we know, isn't it? So now what will be the Q? What will be the Q? The question is we have to find out the rate of heat flow. Okay. Rate of heat flow. Q we have to find out. Okay. Remember how we find out the rate of heat transfer Q in general whenever we have seen the shell balance? So Q is given as flux into area, isn't it? Even though the area of the first term is changing, but since we are looking at steady state, there is no generation, there is no accumulation term. That means what? Q, capital Q is going to remain constant as we move from right hand side to the left hand side, isn't it? In a given geometry, if we move from right hand side to the left hand side, Q is going to remain constant. Capital Q is going to remain constant. Small q, the heat flux is going to change. So Q is going to be constant, and that we can write down directly as area into flux at any x, isn't it? area into flux at any x, because Q is constant. Correct. So that means what? That means what? We can write down this as pi r square into qx at any x, isn't it? Pi r square qx at any x, right? Now, if you go back and check your earlier equation, you can go back and check your earlier equation. Then this is the equation which we had, isn't it? This is the equation we had, correct? So in this particular equation, if I multiply minus k, maybe I just do it here itself. Okay. So in this equation, let's say multiply minus k, then multiply pi and multiply r square, isn't it? If you multiply pi r square into k, so what you are going to get is dt by dr, and what we have multiplied here is minus k into pi r square c1 divided by r square. So what we are going to get, this will be k, this will be q, remember this will be q. So this is given as this r square will get cancelled out. So k pi c1 is going to give me directly the value of q, isn't it? Correct? Are you all able to follow?
Yes, yes.
So k pi c1 is going to give me directly q. In a similar manner, we can write down q is same as this is k1. This is k1. Sorry. So in a similar manner, we can write down this as this is in the block 1, isn't it? So in a similar manner, we can write down this as minus k1 pi c3, isn't it? Isn't it? So K1 C1 is same as K2 C3, isn't it? So we can just write based on this, the expression for the Q can be written directly here as minus K1 pi C1, and this is also same as minus K2 pi C3. Okay. So we can put the values here directly, and by putting the values directly, we can obtain so 3.14, isn't it? 3.14 into K is 5 into C1 is what? The value of C1 is given as minus 2.119. So if you do all the calculation, what you are going to get is 33.3 watt. So is it clear to everyone? Is it clear?
Yes, sir, it is clear.
So this is the answer of part B. Now let's move to part C. In the part C, what is been asked is we have to calculate the heat flux at the open end of the layer 2, isn't it? So heat flux, I can go back and just check. In part C, what we are interested in is part C is the heat flux at the open end of layer 2. That is what we are interested in, isn't it? The open layer of the open end of the layer 2. That means what we wanted to find out the heat flux here, isn't it? So let us write down the expression for that. So heat flux is given by what? What we are interested here is heat flux at open end of layer 2. So that means what we are interested in is Qx at x equals to 0.35. That is what we are interested in. So that will be given by what? What is the heat flux? Q divided by area. So pi r square at x equals to 0.35. So this is nothing but Q divided by pi r2 square. So this we already know Q is 33.3, 3.14 into r square. R is 0.08 whole square. So what you get is what is the value here? Can anybody tell me? What is the value here? So this becomes 1567.04 watt per meter square.
Sir, it should be 6.5. 1657.
1657, correct. 1657. Yes, you are right. (1657.04). Okay. So what is the next part? In part D, what is being asked is, in part D we have to calculate the temperature at the surface of the contact, isn't it? Temperature and the heat flux we have to find out at the, so we have to find out the temperature and heat flux Qx at x equals to 0.2. That is what we are interested in, isn't it? At the point of contact of both the layers. So point of the contact of both the layers means what? X equals to 0.2. We wanted to find out temperature as well as heat flux. So temperature is easy to find out. So T1 can be directly written as 241.2 minus 41.2 divided by 1.1 minus 1.587x. So we can directly put the values here. 241.2 minus 41.2 divided by 1 minus 1.587 into x. In this case is going to be 0.2. So what we are going to get is around 181 degrees Celsius. Is it clear to everyone? So at the contact at x equals to 0.2, T1 equals to same as T2, isn't it? So either you put x equals to 0.2 in equation, the temperature distribution equation for block 1, or you put it in the temperature distribution equation for block 2. Both are going to give you the same answer. T1 equals to 181 degrees Celsius. Is it clear? The second, is it clear to everyone?
Yes, sir.
Yes, sir.
So similarly now Qx can be directly obtained as Qx at x equals to 0.2 we are interested in. So that becomes Q divided by pi r square, and this r square should be at x equals to 0.2, isn't it? So let's find out what is the r at x equals to 0.2. So that can be directly obtained from the equation. Remember what is r? R is related to x as R is related to x by the equation which we have already written earlier. So let me just write down that. So that is 0.18 minus 0.2857x, isn't it? So here x is 0.2. So just put the 0.2 in this equation. What you get is 0.18 minus 0.2857 into 0.2. The x what you are expected to get here is 0.12 28 meter. Just check whether this is correct. So Qx at x equals to 0.2 will be given as 33.3 divided by 3.14 into 0.1228 square, and this should give you 702 watt per meter square. Just check whether this is correct or not. Is it correct?
Yes, sir.
So are you all with us? Everybody able to understand what we are doing? Hello?
Yes, sir.
Is there any question, any doubt, anything you wanted to ask?
Hello, sir.
No, sir, it's clear.
Sir,
Okay, so yes, please go ahead.
Sir, why did we not take QX as a function of R? Why did we take it uniform for an X?
Why we have not taken the QX as a function of
R for a particular
remember,
X?
look at the problem itself, look at the problem statement. Okay, just go back to the figure, then you will probably understand what I'm trying to say. Okay, why we have taken Qx as a function of x instead of R. So here you can see the heat transfer is taking place along the axial direction, it is not taking place along the radial direction.
Yes, sir, I know that, but why did we not, like, as well as X, why is it uniform for a particular X? As we are going, yeah, why is it not varying if we increase or increase the R?
Capital Q you are saying, or small q?
Small q.
Small q is varying as we are moving along the x direction, but across the radial direction, if you are saying in the radial direction, remember there is no heat transfer taking place outside here, isn't it? I understood your question. You are saying that there will be a temperature distribution along the radial direction as well. That is what you are trying to say?
No, sir, I'm actually talking about Qx only, the heat flow that is going in the X direction, but its value, why is it uniform for this cross section? If we take a particular X, so I mean, if we vary R, like, why, yes, sir, like, why is it uniform for X?
At a particular value of x, it is uniform throughout. That is what is being taken because there is insulation outside. But as we move along the x direction, it is varying with the x. So as the x is moving, then your cross sectional area is decreasing, isn't it? And therefore your qx value is going to change because your capital Q remains constant. Capital Q is constant throughout because there is no generation, there is no accumulation term. So whatever is the heat input is taking place from the right hand side, the same amount of heat will come out from the left hand side, isn't it? In between also Q, capital Q is going to remain same, but the small q, the flux, is going to remain constant at each x, but if you move along the axial direction, that is varying. But I think your question is for the same x, why it is not varying along the radial direction, isn't it? That is what the question is.
Yes, sir.
For a fixed x, why it is not varying along the radial direction, isn't it?
Yes, sir.
Okay, so for a time being that we are assuming to be the same, but later on when we will look at more generalized case of the heat transfer where even the convection takes place from the radial direction, in that case you will have a distribution along the radial direction as well. But whatever you are saying is correct. But for a time being we are assuming that it is not varying along the radial direction. We are assuming.
Okay,
Is it
sir.
okay? Okay.
Yes, sir.
But later on a similar type of systems we will see where we will not have any insulation here. Isn't it? And then there is a heat transfer taking place along the radial direction as well. Here why it is not varying along the radial direction? Because there is no heat transfer taking place in a radial direction. There is no heat transfer taking place in a radial direction, and therefore there will not be any temperature distribution along the radial direction. That is why this insulation is put here. This insulation is even though we are not using anything with respect to this insulation here, but this insulation is in the problem statement. This insulation is given in order to make us understand that there is no heat transfer taking place in a radial direction, and therefore there is no distribution along the radial direction. Clear?
Yes, sir.
Okay. But if we remove this insulation here, then definitely we will have a distribution along the radial as well as axial both. Clear? Is it clear?
Yes, sir.
Is there any more question?
Sir, about the slides. So you said you were going.
I have to add only 1 or 2 problems today, and then entire this chapter 1 slides I'm going to upload today. By today night, you will definitely see these slides being uploaded on the Teams. Sorry.
No, sir. Thank you so much.
Because why I'm not doing, because once I stop, once I close this window of my PowerPoint presentation, then all these equations get freezed. So if some equation is not correctly written, then it becomes difficult for me to correct it there. Then I have to write that equation again from the scratch. Okay, so that is why I am keeping this window of my PowerPoint presentation open since last 7 or 8 days. I am not closing it. Once this entire chapter is done, then I am going to put the entire slides for this conduction from the steady state as well as unsteady state, everything in the on the team. Okay, so today you will see it. You will get it today.
All right, sir.
Okay, sorry for the delay, but I hope you guys will bear with me for some more time. Okay, so we stop here unless you have any doubt, any question.